So let's talk about chapter 4. In this chapter, we're going to discover everything about acids, bases, and alkalis. So let's first talk about those acids. What acids have in common is they all contain hydrogen. And some of those hydrogens can separate from the rest of the acid, dissociate, and go into solution as a hydrogen ion. If we had solid hydrochloric acid, a powder for example, and we dissolved it in water, then what we would find is that some of the hydrogens would become separated in the form of this H+ cation. And in that solution, they could then go on to form chemistry with other things. Now this whole idea that the hydrogen ions were responsible for the acidity of acids, it comes from Svante Arrhenius, who you will learn about next year. A H+ ion is essentially a proton, so hydrogen missing its electron doesn't really have a lot more, just this central proton. Now a strong acid will release all of their hydrogen atoms into the solution, and we would call this complete dissociation. A weak acid, on the other hand, would release only a proportion, maybe 1 of 2, or only some of the molecules within that substance would lose their hydrogen and others in that solution would not. This is called a partial dissociation. Now, hydrochloric acid is an example of a strong acid, and ethanoic acid, also known as vinegar, is an example of a weak acid. Look at this tabulated. Complete dissociation occurs in the strong acids like hydrochloric acid, and you can see there what's happening is we are ending up with the one hydrogen that hydrochloric acid has separating from the chloride ion and going its own merry way, whereas in partial dissociation, which we see in weak acids like ethanoic acid, what we can see is only one of the hydrogens, the hydrogen on the end of the COOH group, and not any of the hydrogens attached to the carbon on the other side of the molecule. Only that one hydrogen dissociates. Important to note here that we're not using a single arrow to note the direction of this reaction, because actually in this solution, a weak acid can both dissociate and reassociate again. It's a constant process. Some of those hydrogens are separating and going their own way, and some of them are coming back and reconnecting. And so we use the equilibrium sign. First used, as it says in the section below, by engineer Émile Clapeyron, and then later by Jacobus Henricus van 't Hooft in 1884 in his work on equilibrium. So if you're not an acid, what are you? What's on the other end of the pH scale? Well, you're either going to be a base or an alkali. And what those two words mean is that, yes, you would neutralize an acid if you were mixed together. Bases tend to be insoluble, and so they tend to stay as powders. Even when you mix them in the water, they tend to stay as residue. Whereas a soluble version of the same thing would be an alkali, and so they would go through a filter, and if it was mixed in water, the only way you'd get that back is by crystallization, for example. And that's an important difference. So first, focusing on the bases, these include things like metal oxides, metal hydroxides, and metal carbonates, and ammonia. And we can see here an example of a reaction that sodium hydroxide mixed into water dissociates the hydroxide ion from the sodium ion, and they float around as separate ions. And you can see here on the right hand side, here are some common examples, and they should be straightforward to you, like magnesium oxide, calcium oxide, as an example of a metal oxide, a base. A metal carbonate, they all contain that CO3 group, sodium carbonate and calcium carbonate. Whereas the alkalis quite often involve the hydroxide group, being very soluble, sodium hydroxide, potassium hydroxide, and the rest. These neutralization reactions come with those catchy catchphrases like acid plus base gives salt plus water, But what does that mean? Well, it means we're mixing these two together and we're going to have it neutralize so that the acidic and alkaline properties of these two substances gets cancelled out. But producing a salt and water, what does that mean? Well, first of all, let's look at water's water. We know what water is, but what do we mean by salt? You might be familiar with table salt. That actually is an example of a salt, but there are more salts than just table salt. But you see, we tend to call any compound that is formed by an ionic bond between elements from opposite sides of the periodic table as a salt. And this was what Robert Boyle and Lady Ranelagh, his sister, first used the term salt. It was in this very reaction here that first was used. Acid plus base gives salt plus water. And here is an example below. We've got copper oxide added to sulfuric acid, and it's producing copper sulfate and water. And so the key thing is there's a real clue in the name. The salt, quite often it is composed of a metal from the left-hand side of the periodic table, normally, and a polyatomic ion, a mixture of things most likely from the right-hand side of the periodic table. Now, the non-metal, it has the name of the ion changed from like chlorine to chloride. So there's a slight name change on the end to give that away. So for example, if I had hydrochloric acid, and I mixed it with some like sodium oxide or something like that, then what would happen is the salt I would get would be something like sodium chloride. The chlorine from the hydrochloric acid would bond with the sodium from the metal oxide. And that's actually salt. And so perhaps the reason why Robert Boyle first called it salt was perhaps because the very first example of this produced table salt. And he could identify that really easily just by tasting it. Other examples include sulfuric acid. That could produce something like sodium sulfate with the SO4 group on the end. Nitric acid could produce calcium nitrate with two sets of the NO3 ion on the end. Ethanoic acid, vinegar, could produce something like ammonium ethanoate, which is getting quite complicated. More of that later. If it was true that an acid plus a base gave salt plus water, and we said that all alkalis are in fact bases, well then it's also going to be true that an acid plus an alkali is going to give salt and water. Here's a nice example. Hydrochloric acid added to sodium hydroxide produces our good old friend sodium chloride, table salt, and water. Now sometimes we would write out the full equation like this, but sometimes it's more convenient to show an ionic equation, which basically shows just those ions that are involved. Here we're concentrating on the neutralization of the H plus and the OH minus to form water. That is sometimes how it's going to be displayed, just because it's more convenient. Several slides ago, we spoke about the bases and how the metal oxides were bases. We also said the metal carbonates, the CO3 ion attached to a metal, could also go on and be a base. Well, here is that example. Now, it's exactly the same as before. It produces salt plus water, with the exception of it also producing a third product. Where does the carbon and the oxygen go in that carbonate? Well, it ends up as a carbon dioxide molecule, which is also given off. Here's a nice example of that. An acid plus a carbonate gives salt and water and carbon dioxide. If we had sulfuric acid and we added it to zinc carbonate, a white powder, then we would end up with some really nice crystals of zinc sulfate, some water, and carbon dioxide gas, which could be detected by bubbling it through lime water and having it go cloudy. The key thing is that we've got carbon dioxide gas given off. That's because it's a carbonate. Talk about the strange case of sulfuric acid. The sulfuric acid has been known about since the 9th century, and we think it was Jabir ibn Hayyan who was the first person to mention oil of vitriol. Vitriol was the name the alchemists gave to anything that contained the sulfide ion, basically. So we had like blue vitriol was copper sulfate and green vitriol was iron sulfate. And if you heated them up enough, you would probably be able to extract some oil of vitriol, sulfuric acid. Now, the reason why it's such an odd duck is, in this case, it acts both as a strong and as a weak acid. The first hydrogen that is dissociated from the molecule is removed really easily and readily and completely, making it a strong acid. And that's because before it is removed, it is a strongly polar molecule, and water, being a polar solvent, is able to break that up. But having removed the first hydrogen, it is then not so nearly as polar, and water's powers are severely limited. It can't attack because it's no longer polar, and water, being a polar solvent, can't do much about that. So the second hydrogen is only sometimes removed, and in other times it's put back again. And so that equilibrium, that kind of the constant back and forwards of hydrogens dissociating and reassociating that we see in a weak acid happens with that second hydrogen. So yes, it is a strong acid in that it readily gives up its first hydrogen, and it's a weak acid because it only partially dissociates its second hydrogen. There are other acids out there like this, such as phosphoric acid.